Hey there. In this video, I just want to walk through the graphing and summarizing data PowerPoint with you. I'm just going to kind of go through and hit the high points. You can go through it, and if you open it actually in PowerPoint, there are additional notes in the notes feature in there. But I was just going to sort of walk you through and, like I said, hit the high points. In this module, we're going to talk a lot about how do we describe data, how do we summarize the data that we have. You might hear these called like descriptive statistics because we're basically just describing our sample. And what are different ways that we can do that? One way is using a percentile. You may see me call them p-tiles. I'm just talking about a percentile here. And basically, this is some way to represent how one score is relative to other scores in the distribution. So in this example, say you scored a 35 out of 50 on some measure of anxiety. Does that mean you're anxious? It's hard to know without more information. Sometimes a raw score can just be hard to interpret. So you might turn that raw score into a percentile, and you can say how you did, how that score is relative to other scores in the distribution. So if your percentile was, you were in the 65th percentile, then that means that you scored at or higher than 65% of the others people in the sample, or if it's like a normative group, 65% of the population. It tells how you did relative to others who have taken this same test or assessment, whatever it is. We're also going to talk a little bit in this about, distributions of statistical data. How do we represent, how do we describe sort of the data that we have? If we have a discrete variable or a variable that takes on only certain categories, we might use a frequency table or a bar chart. If we have a variable that's continuous, so it takes on a range of values, then we would want to use a different type of way of describing them. So a very common technique of describing data is just a frequency table. You'll hear people talk about running frequencies on their variables. They're talking about doing a frequency table here. Like this is a frequency table of someone's favorite, we ask people what their favorite color is. And so this is basically just a frequency table. It's a printout from SPSS actually. That tells you the different categories of the variable. So people could choose whether their favorite color was red, blue, green, or yellow. And you can see 11 people chose red. That was around 26% of the sample chose red. 15 people chose blue. That was around 35% of the sample. It also gives you the total. So we see here 43% there were 43 people who we surveyed, I guess, and asked for their favorite color. And so the percent is just based on the frequency divided by the total. The valid percent and the percent would be different if we had missing data. Say, we actually surveyed 45 people, but 2 people didn't respond to what their favorite color was. The valid percent would be based only on those who replied to the question. So those who had a valid case on it, where the percent would be based on the grand total. The cumulative percent just adds that category plus every previous category. So see, the first category is always the same as the percent. The 60.5 would be if we added 25.6 and 34.9. That's what the cumulative is. And in the last category, the cumulative should always equal 100%. So the golden rule of data analysis, the first rule of data analysis should always be run frequencies on your data. That should be one of the first things you do. It's the best way to identify any type of mistakes or coding errors you might have in your data set. You'll notice your variable has like missing labels. Say, we ran a frequency, we noticed number 2 didn't have, say, blue. We'd have to go back and figure out, well, what did 2 represent? For the, maybe we'd go back to the survey or whatever the instrument was, and we could correct that. That's what running frequencies on your data helps you identify any type of coding mistakes. Or say we only allowed 4 categories, but then we had somebody here labeled a 6. Oh, well, that some type of coding entry. We'd try to figure out what was going on there. So it's always important to run frequencies on your data to make sure everything is how they should be with your data. Sometimes people will use like a 9 or like a -99 or something to indicate a missing value. And so you wouldn't want to create an average of that variable, say if it had -99 representing a missing value. So if you run the frequencies on that, you'd notice that that was coded as a valid case, and you could go back and code it as missing. So running frequencies should always be the first rule of any data analysis. Before you run anything else, before you run your t-test or any other analysis, run a frequency on all the variables that you're going to use, just to make sure everything is coded correctly. The second rule is then graph your data. You should always graph your data to get a visual representation of what your data actually looks like. And so if you have discrete data, like you might hear it also called like categorical data, like our color, like what your favorite color is, you could represent that with a bar chart. So here's just a standard bar chart you can get out of SPSS, and I have another video on Canvas that will show you how to get these out of SPSS. But you can see this just has the count. Remember, there were 11 people who chose red, and so the bar goes up here a little past 10 for 11. So for continuous variables, and you'll notice this in SPSS, it's difficult to represent with a frequency table. And if you run a frequency in, say, SPSS with a continuous variable, you'll just get a really long table. And so it would, can kind of be, it's not as useful. Frequencies aren't with continuous variables, but it could be good to check out the minimum and maximum, make sure they're within the range maybe that they should be. So this is when graphing the distribution might be more helpful, and we'll show that. I'll show that in a minute. I thought that was next. What you would do if you were maybe presenting a frequency table for a continuous variable, say in a report, you might want to do what they call like a grouped frequency distribution. So you would just group them, 500 to 600 range, 600 to 700 range, and the count that's within that range. That might be a more useful representation than just listing each of them. So typically in mathematical statistics, we'll represent statistical distributions using mathematical equations. So this equation I'm showing here is the equation for a normal distribution, where mu here would represent the mean of the distribution and sigma here would represent the standard deviation. So if we look here, a normal shaped distribution is what we would call a like bell-shaped curve. And we'll talk in, is it the next module on probability distributions, why the normal distribution is so important in statistics. There's a theorem called the central limit theorem that makes the normal distribution very important. It basically says that the sum of independent random variables will approximate a normal distribution as the sample size increases. So if we continuously, basically it says if we continuously sample from a distribution and calculate the mean for each of those distributions, and the sampling distribution of the mean would approximate a normal distribution. But we'll get into that in that section. You don't have to worry about that right now. But the mu here would define where the distribution is along this x-axis. So we would change this and it would move this distribution along this axis, along the x-axis. The sigma here would define like how spread out this distribution is, how variable is it. This blue distribution would have a smaller standard deviation than this red distribution. Typically, we talk about the symmetry of a distribution, and the symmetry just means, you know, we could fold one half of this distribution of the other, and it would fit. It would be symmetrical, right? And so we talk about the skewness of a distribution is a measure of how symmetrical that distribution is. You know, distributions aren't often perfectly symmetrical like this. They're usually skewed in some way or another. And a positively skewed distribution means that we have like outlying cases, or we have our over in the positive side of the distribution, the right side, there's more cases than there are on the left side. So it's positively skewed. The tail is pointing in the positive direction here. And the negative skewed is just the other way. There's a larger concentration of data over here on the left side of the distribution, which is skewing the distribution to the left. So we have a measure of, there's actually a skewness coefficient that we'll talk about that talks to us, that kind of gives us a numerical representation of how asymmetrical the distribution is. If the skewness coefficient is 0, then that indicates that the distribution is perfectly symmetrical. If it's positive, it's saying that it's positively skewed. It's negative, it's saying it's negatively skewed. And generally, we're not too worried. You know, we might have a little bit of skew, but it's probably not too much to worry about. We're never going to have a perfect, say, normally shaped distribution. But, you know, how far away from normal do we have to be before we're really that worried about it? That's what we'll kind of talk about. Kurtosis is sort of a measure of like the peakedness of the distribution. And you can also think of it about how heavily tailed the distribution is. So a normal distribution would have no kurtosis. So it might have a kurtosis value of 0. A leprechaunic distribution, you can think of it about as leaping. It has a high center. What it's saying is there's few cases in the tails of the distribution. That would be a leptokurtic distribution. There's more in the center than there are in the tails. And then a platykurtic distribution would be that there's a lot of data in the tails of the distribution, so it's flatter. There's not as much in the center of the distribution. And so that would be represented with a negative kurtosis value, and a leprechaunic would have a positive kurtosis value. And depending on the software, SPSS centers the kurtosis value at 0, so 0 represent normal. Other software will use a kurtosis value of 3 as a normal distribution. So sometimes you have to just read up in your statistical package manual to see, you know, that's why also graphing the data give you a visual representation, so you'll know beforehand, sort of before you actually run that statistic, what maybe you could expect for both the skewness and kurtosis value. So different ways of graphing data. You know, I'm sure everybody's seen a pie chart before. I'm not a big fan of pie charts. I don't think pie charts are a very effective way of displaying information. It's probably effective for 3 or fewer categories, I would say. Anything more than that is really hard. It's really hard because you're basically trying to judge the angle of the of each piece of pie. and that's hard to judge visually. I love this quote from Edward Tufte's The Visual Display of Quantitative Information book. You know, a table is nearly always better than a dumb pie chart. The only worse design than a pie chart is several of them. So you can see that Edward Tufte also doesn't agree that pie charts are very effective ways of displaying information. I always think a bar chart would do it just fine. And to me, it's a lot easier to compare the size of these bars than it is to compare the angles in this pie chart. So that's my but you know, I'll be okay if there's 3 or fewer categories. Usually that's okay to display in a pie chart, but only when it's a few categories. Bar charts are also really good at comparing differences between 2 groups. So for like males and females, we can stack the bars on top of each other. It's a great way to compare them. You might also hear these called column charts versus a bar chart, but I'm just going to refer to them both as bar charts. Here's some mistakes, you know, try to avoid, you know, try to keep the, you know, don't distort the difference between the sizes. Look at how this interest rate chart is distorted. Now it looks like interest rates soared between 2008 and 2012, when really there was very little movement. You know, it went from a 3.14 to a 3.15. So it's not a very large increase in the interest rate, but this graph really distorts that, while when we anchor the graph at 0, we see that it is basically flat. You can also, I've also linked here to a really cool Wikipedia page of misleading graphs that you can sort of check out. I thought this was just a funny comment. You know, I think we should give it another shot. No, we should break up. I can prove it. She has this graph of their relationship. He looks at it and goes, you know, you're right. I knew this data would convince you. No, I just think I can do better than someone who doesn't label her axes. See, we don't know we know the relationship. It looks like the trend's going down, but what does this represent? We don't know what the X and Y axes represent here. So, you know, bar charts, column charts are good for graphing categorical or discrete data. You know, we could also, you know, do it for more like quantitative variables, continuous variables. We can have a stem and leaf plot. I think these are probably kind of going out of favor. They were really, you know, before computers, when you were, you know, graphing things, you know, distribution by hand, a stem and leaf plot was a really neat way of visualizing your data. You get the same thing from a histogram. You know, here, you know, the stem is a 7, and then there's each leaf a bit. So these were, you know, this would be 100. You know, there were 2 100s. There was 190, 191, 198. There was 172, 272s, a 74 in this distribution, a 75 in the distribution. It could be good for representing small to moderate amounts of data. It kind of gives you a display of the distribution. I think the histogram does the same thing. You know, here's a histogram from SPSS with a normal curve laid over it. So you can see these data here are pretty normally distributed. It might have a little bit of negative skew to it, but, you know, we would look at this and say it was pretty fairly normally distributed. I wouldn't be too worried about that data. If I needed the data to be normally distributed, I wouldn't be too worried about these data. Here's some other like frequency polygons. You know, you can see here we have the histogram, and then the frequency polygon basically is just taking like the center point and graphing it. So each dot on here would be where the histogram bar would go up to. And so usually this is a lot cooler way. It makes it a lot easier if you're going to compare two distributions. So instead of putting the two frequency histograms on top of one another and there'd be a lot of overlap, you could use this polygon here and you can really compare the distribution. So it looks like the blue distribution, this target distribution, the time is a lot quicker than those in the small target or the red distribution. So it serves the same purpose, but it's good for comparing distributions. Box plots are also really good at comparing distributions and for identifying extreme cases or outlying cases. The box here usually represents what we call like the interquartile range. So this is where about half of the scores in the distribution lie within this range. The line typically represents the median. Sometimes you'll see people put a dot in there to represent the mean of the distribution. So the median is the 50th percentile, so the point in the distribution where 50 or less than half of the cases are less than that point. The first quartile is the 25th percentile, and the third quartile is the 75th percentile. A lot of times, depending on the program, the whiskers represent different things. Some people will set the whiskers out to the minimum and maximum value. Sometimes you'll see the whiskers set out to the 5th percentile and the 95th percentile. Sometimes you'll see the whiskers represent the 1.5 times the interquartile range. And sometimes you'll see a definition of an outlier as anything that's more than 1.5 times the interquartile range. And what we mean by the interquartile range is basically the third quartile minus the first quartile. So that's the how we would define the interquartile range statistic. Here's a diagram of how SPSS defines the box plot. So you can see what it's representing. So the red dots here are the actual data points. The median here you can see is represented with a solid black line. So half of the sample will be above this black line, the other half of the sample will be below this black line. Within this red area is the interquartile range. So this would be the lower quartile, the 25th percentile. This would be the upper quartile, the 75th percentile. The whiskers here will represent 1.5 times the interquartile, right? What does it say? The largest unbooked sample value. So I think so what it's calling as the book sample value is I think this box length here. And so it's taken, so 1.5 here's 1.5 times the box length or 1.5 times the interquartile range would be here. So this is the largest sample value that's neither an outlier nor an extreme. And the same thing here, this is the smallest sample value that's neither an outlier nor an extreme. And so it's going to define an outlier as anything that is greater than 1.5 times the interquartile range. So the whisker only extends here because this is the largest sample value that's not greater than 1.5 times the interquartile range. It's going to represent anything with an outlier with a hollow dot, and anything that's more than 3 times the interquartile range, it's going to represent with a star on the outside. So it's going to say that's an extreme outlier. It's vastly different than the rest of the sample. So that's how SPSS defines the box plot. So if you get a box plot in SPSS, you know what the whiskers represent, and then you know what the hollow and the star dots represent. You can see a normal distribution in a box plot, will be fairly symmetrical. you can see if it's, the positive skew is going to have more data over here on the positive side. And then the negative skew, you can see that there's more data over here on the negative side. And you can see that by the fact that the box plot is sort of moving in that direction. Because remember, half the data are below the median, and then the other half of the data are above the median. So you can see that more than half, look at all these data points that are below the median value. So you can see here, box plots for comparing distributions and identifying outliers. So this is the age of Oscar-winning actors from 1975 to 2004. So you can see that the females tend to be younger, and then the male actors tend to be older, the winners. So you can see how you can kind of compare the distribution. And then you see sort of the outlying cases that are a lot different. This female who's about 60 was in line with basically the distribution of males, but is an outlier compared to females. Line graphs here, they're really cool for especially displaying ordered data, or data that have an ordering on the x-axis. Especially if it's time in some way, and you can see change over time. Dot plots are another cool way, instead of, I guess, doing it kind of displays the same information that a bar chart or a column chart, and, can also be used to compare distributions. There's a lot more information on graphing data. If you go to the Canvas site, so if you go to the Canvas site here, there's some cool, this chart guide. I think it's really cool. It has, you can you not download it? I may have, yeah, here we go. You can see, what's good for showing comparisons between categories. It gives you lots of different information for showing things, and even, tips and suggestions for things to avoid. Show a distribution of your data. Look, there's our like frequency distribution. There's our histogram. We didn't talk about like violin plots, but they're very similar to what a dot plot. So your dot plots. We want to show the relationship between elements. Here are different ways we could do it. Show relations, the part of the whole. So it'd be similar to a pie chart. And look, he kind of grays out ones that he doesn't like in here versus some other cool way. So I thought that would be a good way of showcasing. I kind of keep this handy, and I have this actually printed out and hung up on my bulletin board. So when I'm actually looking at data, I can refer to it to see, okay, what are some different ideas. You can also look at this data visualization handout. It gives you some really cool tips and pointers for displaying data and things to do and things not to do. Like this is something we wouldn't want to do. That just leads to, there's not one best graph. Deciding what kind of graph is best to display requires a lot of judgment on your part. Think about what's the best way to communicate the message that you're trying to get across. I think not this next academic year, but the next, we're going to actually our department's going to offer a course just on data visualization. So keep your eyes out for that. Let's see, you can graph data both in SPS and Excel. I really prefer Excel. I think it's a lot more flexible, has a lot more options for doing that. SPSS, I would only use it to maybe get a quick view of what my data might look like. But if I really want to present something I'm going to present either in a research report to a client, something I would typically use Excel because it can make them a lot more visually pleasing in Excel than you can do in SPSS. In SPSS, you tip on graphs, legacy dialogues, and you can select bar chart, histogram. You can get a frequency, a histogram from the frequency command, and I have a video that I'll show you kind of walk through how to do some of those. The explore command, you can get the stem and leaf in a histogram plot in there. So, you can check those out and see. So, now when we talk about, which ways can we numerically kind of summarize our data? And that's where like descriptive statistics try to offer, one or more numerical values that sort of summarize what our data will look like. So the central tendency, by central tendency, we just ask, kind of what's the center of the distribution? What single score best represents this entire distribution? The three most common measures of central tendency are mean, median, and mode. And while sort of on the activity in this class, and I'm going to kind of talk through here about, what's the best score that represents this distribution. We'll focus on a single score, but really in practice, sometimes we'll give multiple of these measures because one measure probably doesn't do it justice. So we might present both the median and the mean or the mode of the distribution. But you'll see that as we talk about these, some of these are more appropriate in different situations. When statisticians use the word mean, they're just talking about the arithmetic average. So we add up all the values and divide by the total number. That's all it is. It's just the arithmetic average. We call it the mean. It's the most common measure of central tendency. And you see it reported a lot. So different books will use different, you'll see this Y bar or X bar or just an M to represent the sample mean. And then we'll use the Greek letter mu here to represent the population mean. Typically in statistics, we'll use Latin characters like Y, X, or M to represent sample values. And we'll use Greek letters to represent population parameters. So mu would be a population parameter. It would be the population mean. Here's some different characteristics of the mean and why the mean sometimes isn't a good measure of central tendency. So, if we change a score, it'll change the mean, right? And, if we add, subtract, or multiply or divide every score by a constant, the mean will change by that constant. So we multiply each score by 2 is the same thing as multiplying the mean of that distribution by 2. This is really important. The mean is highly susceptible to outliers or extreme data points. That's what makes the mean not as good. The mean is a good representation for a distribution that doesn't have very many outliers or a distribution that isn't highly skewed. A better representation of a skewed distribution might be the median. It's just the midpoint of scores. The median always corresponds to a percentile rank of 50. It's appropriate to use with ordinal data, and it's appropriate to use when you have extreme scores and when the distribution is skewed. Usually we'll default to using the mean, especially if it is continuous data, except if the distribution is is skewed in some way or has some extreme scores or outliers, then we'll use the median as the measure of central tendency. So in this distribution, we see, look at this, that we have a 3, a 4, a 4, a 5, and a 24. So the middle value, if we do 1, to get the median, we basically just put the the numbers in order in the distribution and look for the center number. So the 50th percentile here, the middle number, the midpoint of the distribution would be 4, whereas the mean of this distribution is 8. You know, if we look at the vast majority of numbers in this distribution, it looks like, you know, they're most of them more similar to 4 than they are to 8. You know, which number best represents this distribution, I would probably argue is the median versus the mean. The mean gets pulled in the direction of the skew. So the median sometimes is a better representation of the middle of the distribution. When we have two numbers that are both in the middle of the distribution, like we do here, we would typically average those two numbers and use that as the mean. The mode is just the distribution that occurs most often. The mode is most appropriate when you have nominal data. So if we have categorical data or discrete data, we would use the mode as the measure of central tendency. It's just basically defined as the most frequent score in a distribution. We sometimes talk about the distribution being unimodal, so it only has one mode. Bimodal, it has two modes. Trimodal, it has three modes, or multimodal, where it has more than three modes. Like here, this may be a trimodal distribution. And sometimes you'll hear people talk about like major modes, minor modes, you know, that this one, it really looks like there's three distinct peaks to this distribution. So I would say it would be trimodal here. You could also think of this as being the main mode because it's the score that occurs the most often. You see that it has the highest frequency. But really, you could think of this as being a trimode. There's three distinct peaks in this distribution. That's what's really going on with the mode. You can see if you have a perfectly normal distribution, the mean, median, and mode will be perfectly aligned. So that's one way to present all three numbers. You can kind of tell whether the whether the distribution is normally distributed or not. With a left skew, you see that the mean is pulled towards the direction of the skew. Same thing with a right skew, the mean is pulled in the direction of the skew. So here, if the mean is less than the median, then that's usually an indication the distribution is negatively skewed. When the mean is greater than the median, that's typically an indication that the distribution is positively skewed. Another big measure, another important descriptive statistic is one that measures variability or the degree to which the scores are spread out in the distribution. And so, you know, variability is, you know, I like to think of it as like your best friend in statistics, because if things didn't vary, we wouldn't have anything to study, right? Everybody would be the same. And so just like we have many different measures of central tendency, we have different measures of variability. So the range is just basically the high score minus the lowest score. Some books you'll see it defined as high score minus the lowest score plus 1. They're still trying to get at the range. The range is really used as a measure of variability, and it's more common really to just report what the minimum and maximum values are. The interquartile range, we sort of already talked about it. You know, it's the range of the middle 50% of scores. And it's defined as the 75th percentile minus the 25th percentile. The interquartile range is a good representation of variability when the distribution is highly skewed in one direction or the other, because it still gives you the range of scores in the middle 50% of the distribution. The interquartile range is also useful for identifying outliers, just like, you know, typically a common way we'll define an outlier is anything that's more than 1.5 times the interquartile range. Usually doesn't mean that that value is necessarily an outlier, but it probably says that value deserves some extra scrutiny. You know, what's going on? Was this some type of coding mistake? Is this a valid case? Maybe what's going on with that value? The variance here is basically the average of the sum of squared deviations around the mean. So we take each value, subtract it from the mean, square it, and do that for every value, and divide by the total number. So that's how we would calculate, we represent variance in a population with the Greek letter sigma, so it'd be sigma squared. In the sample, we use just the letter S, and so it'd be S squared. And so we take each sample value, subtract it from the mean, square it, sum across do that for every data point in the sample, and divide by n-1. There is a good discussion in the Gravitier and Walnu book about why we divide by n-1. It's basically, it makes a correction for that if we didn't divide by that in the sample, our variance would be overly biased. And so this sorts of corrects for that bias, and you can read about that in the book. So if you have the 10th edition of the book, they talk about why we divide by n-1 in section 4.5, sample variance as an unbiased statistic. It's on page 117, and you can see that the dividing by the n-1, and there they have a nice walkthrough about how it reduces the bias in that estimate. Usually we don't use the sample variance that much. We typically will take the square root of this value and report what's called the standard deviation. This is probably the most common measure of variability. It's especially useful. So whenever you're reporting a mean, I would report the standard deviation that goes along with the mean, because notice that the variance and standard deviation are based on deviations from the mean. So if the mean isn't an appropriate measure of central tendency, then the variance or standard deviation isn't an appropriate measure of variability, since we're taking deviations from the mean. The standard deviation is used, and so since we're taking the square root, we take the square root on both sides. So the sample standard deviation, it would represent it with just an S, and then the population standard deviation would just use sigma. The standard deviation is usually reported because the variance is in squared deviations from the mean. So if we take the square root of it, we put it back in the same units of measurement as the values in the data set. So that's why we typically like using standard deviations are usually easier to interpret than talking about squared units. However, the squared deviations have some nice mathematical properties that we're going to use later on and take advantage of when we talk about like analysis of variance and stuff. Here's, here I'm just walking through, basically, here's our raw data, this X column. So we can see we have 90, 85, 76, 75, 75, 70, 65, 49. If we take the average of all of these, the mean, we add up each one, divide by the total number of 8, we get 72. We see that the median number is also 72. It looks like the median is 75. I should change that. So the median should be 75 here. So that's not right. But to calculate the variance and standard deviation, we take each data point, subtract it from the mean. So 90 minus 72, 85 minus 72, 76 minus 72, and then we square each one of those. Right, so this is where it's in the squared units. Because if we added up each deviation from the mean, you see the sum is 0. So that's not helpful. So that's why we would square them. And then we add up each of these squared deviations. That's why they're called sum of squares. And so we would take all those, divide by the total number minus 1. And so the variance of this sample would be 229.1. That's not as easy to interpret as if we took the square root of it. So we could see that on average, you know, each data point in here varies from one another by around 15 units. So that's the average deviation from the mean is about 15 units. So how do I pick one to use? Like I said, a lot of times this deals with like the type of data you have. You know, if it's continuous data, we could use the mean, median, or mode. If we have categorical data or discrete data, the mean and median don't make sense in those situations. Same thing, you know, if the distribution is highly skewed, we would take the median over the mean. We'd also probably report the interquartile range if the distribution was skewed instead of reporting the standard deviation, since the standard deviation is based on the mean. So I kind of give you some, a little scenarios about, you know, recommendations about when you would pick one or the other. You can read about different properties of the standard deviation. Some nice properties of the standard deviation, especially in terms of its relationship with the normal distribution. So if your distribution of data are normally distributed, then around 68% of cases will fall within one standard deviation of the mean. Around 95% of cases will fall within 2 standard deviations of the mean. And almost a little over 99% of data will fall within 3 standard deviations of the mean. So it's very rare if the data are normally distributed to have individual cases that are more than 3 standard deviations greater than mean. So those are just some nice properties of standard deviations. That's why they're very useful for describing distributions, especially when the data are normally distributed. I'm going to let you work through the rest of this. There's some practice exercises. If you open this up in PowerPoint, the answers are in the notes section. So I'll let you look through all of those. And be sure to check out the practice data activity on Canvas. As always, if you have any questions or troubles, shoot me an email, and I'll be happy to help you out. Thank you.